Okay, so yeah, so welcome everyone, and I encourage that you ask as many questions as possible in order to make the best, take the most benefit out of this session. Okay, so with that, I will start and share my screen. Okay, so there are two parts of this talk. One is about gradient descent, which is an optimization algorithm, and second is talking about decision tree. So I was thinking, I mean, if Dr. Suren permits, so I was thinking like, can I take, let's say, gradient descent followed by its hands-on in the first half, and then decision tree, and then followed by its hands-on in the next session in the
Yes, sir.
afternoon,
Absolutely fine, sir.
so that
As per your
this,
convenience, as per your thought, just you take as per your
yeah,
convenience. Not an issue, sir.
okay, yeah, okay. I hope my screen is visible to everyone.
Yes, sir. Yes, sir.
Okay. All right. So before actually I jump into and talk about what is gradient descent, so I think all of you had a session on linear regression, right?
Yes, sir. Yes, sir.
So, so gradient descent, let me tell you, give a brief primer of it, and then tell you, actually, I will motivate you why we require this. Okay, and before we go and build a general gradient descent algorithm for any cost function, let us talk about a concrete example, right? And then see the need of it, why we need gradient descent. Okay, so all of you know linear regression, yes? So so hypotheses are the prediction rule for linear regression model can be written like this. Okay. Or sometimes you must have seen prediction rule or cost function written this h theta x. Just a second. Okay. You must have seen maybe this form, right? Summation I equal to 1 to n. Then let's say sometimes you written like this theta transpose x I minus yi squared. Okay. Yes. So audience, here is a question for you. If you don't ask question, I will ask questions. All right. So what what is the name of this loss function? We have a name for it. Okay. Okay. Anyone can tell me the name of this loss function? Okay. Ordinary list is square. That's the name of the prediction model, right? Linear regression model. So here I am interested in knowing this name of the loss function, right? So this loss function is popularly called, okay, mean squared loss, okay, MSC, mean squared loss function. Okay, that's the loss function we optimize in a linear regression model. Yes. Okay. And this loss function on your screen, this one is actually same loss function written in a vectorized form, or in the case of matrix in vector form. Okay. So I don't know, I mean, what kind of loss function you had seen in the linear regression model, but this is the one that we use. Okay. And if you write this loss function in the case of matrix, so it will look like this. Okay. S theta x equal to x theta, where x is the matrix of input features. Okay. And what are the input features? Let's say you are building a house prediction model. So x is nothing but your data matrix. Okay. Let's say this size of the house, number of bedrooms, okay, number of bedrooms, and y could be the price of the house. Okay, so x will contain this data. All right, and theta is the parameter, means the model in linear regression that we want to learn. Okay, and s theta x is the vector of predictions that we want to predict. Yes. Now, I hope this should be easy for you since you had a session on it. Yes, participant can tell me, type in the chat box that they already know these things so that I don't spend much time on it. Okay. So write in the chat box that you are familiar with this one. Okay. Yeah, fine. So quickly recall. Dr. Kalaipriya. Okay. Yeah, so this is fine. I mean, I think this should be familiar to you. Okay. Um, all right. So now, and how about your familiarity with matrix and vector? I hope you know what is a vector and what is a matrix. Is that fine? Okay, so everyone knows, I believe they know what is a vector and matrix, right? Okay, great. Then, so this would be an exercise for you, or maybe Dr. Surendra, you can put this in your questions. 5 questions I had sent, right? So
Yes, sir.
how to convert this loss function into this vector and matrix form? So the equivalence. Okay.
Sure, sir.
Yeah. So that would be a good question to work out. Okay. So take my word as granted, saying that these two equations, okay, one in the scalar form and second this is vector form, they are same. Okay. Now you have to, let's say, find this theta. Okay, that's our let's go to the next slide. Okay. So vectorized cost function. Sorry, actually I did a one wrong thing. I should not say. Just a second. Uh, okay. So actually they are not at this moment. They are not the same. Actually, the idea is this is your model. Okay, linear regression model. So this is actually same as what you have to do. Show me this one. Like this model you see here. This is same as saying yes theta x equal to let's say we write like this summation over 1 to n, then we write theta transpose xi. Okay. um okay, so actually this loss function, rather than showing the equivalence with so this is your actually model, linear regression model. Okay, and even I should not, this is cluttering my slide. Okay, just a second. So this is your linear regression model. Okay, just to start with, if you recall, linear regression model, very simple linear regression model is given by this one. Linear regression is nothing but using a line to predict your data. Okay, so all of you know this equation, y equal to mx plus c. So this equation of a line sometimes written in more general form, and we call it theta transpose x plus theta 0. Okay, so you can compare your linear regression equation, this equation of a line, which is same as this one in a higher dimensional space, right? So in 2D xy plane, we write the equation of a line using y equal to mx plus c. But in higher dimensional space, let's say 3D and higher dimensional, we use equation like this: theta transpose x plus theta 0, where theta 0 is the intercept and theta is your um, parameters. Okay, besides this theta 0 is also part of parameter, and together this is same as written sometimes if you observe, sometimes we observe okay, we observe this theta 0 within this theta itself, we write in a neat form theta transpose x. Okay, so that is our model. Okay, so this is our model, not the loss function. Basically, the exercise that you have to do is this one. Okay, so the loss function, mean squared loss function, you have to show that this loss function is same as this one. Okay. Theta transpose xi minus yi. Okay. So we have to show that this mean square loss is same as this one. Okay. By mistake, I said that one. Sorry for that. Okay. So you have to show this equivalence. Okay. For now, assume that they are equivalent. Now, this is your loss function or cost function. Okay. Now, tell me how do you compute the, you know, how do you minimize this loss? In many of these optimization machine learning, we have to minimize this loss function, right? Minimize the loss. What is your optimization variable? Theta. Theta is unknown, right? When you optimize that, that means to find the unknown parameter theta. Okay. So how do you find this unknown parameter theta? By minimizing this function. Okay. So how do you take minimize this function? Anyone can tell me how do you go ahead and minimize this function? Or what will be the minimum? Any ideas? Yeah. We basically, we don't need partial derivative because there is a single variable. Okay. We take the partial derivative when there are more than one unknown variable. Okay. Or you can also say, because the theta is a vector of variables, so you can also say we take the derivative of loss function with respect to theta and set it to 0. Okay. So what you get is this. Okay. Another exercise for you would be, show me that the derivative of this loss function, let's say call it equation number 1, is this one. Okay, the partial derivative with respect to theta is this one. This is another exercise. I believe that most of you know the calculus, so you can take the derivative. But this is advanced calculus. This is not the same as what you have learned. In 10 plus 2, we study single variable or two variable derivative, right? But there are more than one variables, and it is more of matrix and vector derivative. So you need what is called multivariate calculus. If you want to understand how this derivative is computed, then you need to understand multivariate calculus. Okay, multivariate calculus. So you'll get this one. Okay. Now, if you set this gradient to 0, that what one of you pointed out, then this will give me this one. Okay. And eventually this will simplify to this one. Okay. Upon solving which we get, if you solve this for theta, then you will get theta x transpose x inverse x transpose y. That is my solution to linear regression problem. Okay, that should be familiar to you. Okay, fine. Or maybe, I don't know, I mean, whether you had seen this equation in your linear regression course, or maybe in linear regression course, what you had seen was theta 0 computed as a covariance of x and y divided by the variance of x. Okay. So maybe, so tell me, like, which equation you have seen in linear regression problem. Okay. Okay. So maybe this equation might be familiar to you, or not this one. Anyone can confirm whether you had seen equation, this green equation or this blue equation? In linear regression, when you solve, then you get these equations, right? Now see what is the issue. Why we need actually gradient descent. Okay. Because when you study something, you should know why it is required. Okay, not just that, okay, gradient descent invented someone and I will study it. It's not like that. You basically see why, whatever the issue in this equation, let's say blue equation, that we required actually iterative optimization algorithm. Okay, fine. So anyone can tell me, like, if you solve this equation, blue one, okay, what is the issue in this equation? Why don't we use, I mean, we got the closed form solution for the unknown parameter theta, given this data matrix X and a label features in the sorry, X is your data matrix, Y is the labels, okay, the Y target values. We can go ahead and compute the theta value directly, right? Yes. Then why we don't use this equation? Why we need gradient descent? Anyone can give some intuition? Any ideas? Okay, so GOT is saying many multiplications are involved. So complexity is high when many input features are there. Very good. Yes. So that's the issue. Like if you see how many matrix multiplications we have, we within the bracket we have one matrix multiplication, and after that we have to invert. Okay, and then again multiply with another matrix, and then another vector multiplication. So okay, so it's a really problematic. I mean, it's very computationally demanding, especially when data matrix X is very large. Okay, you have large data, a big data, then computing this theta using this method is, it will take a lot of time. Okay, so as a practical exercise, what you do, you go ahead and I hope in the hands-on session of linear regression, you must have implemented this equation. Okay, so what you do, you take a data matrix. In that you have, let's say, 1 million samples. Okay, and maybe 50 to 100 features. Take any randomly created data matrix of this size. Okay, let me uh, exercise for you would be, take a data matrix X of size, let's say 1 million into 100. Okay, 1 million samples and 100 features. Okay. Yeah. So you take this data matrix and try to learn linear regression model in Python. And note down the complexity. Okay. Okay. Note down the complexity. Take this data matrix X and run linear regression. Okay. That when I'm saying run linear regression, that means compute theta using using this equation. Okay, X transpose X inverse X transpose Y, and note down the time, how long it takes. Okay, after that, okay, now we have seen that it is very computationally demanding. So here is the reasoning. Okay, what is the issue with this equation and why we don't use that for big data? Okay, one is that if the matrix is not invertible, it is possible that this matrix after multiplication X transpose Y, it is non-invertible. You cannot invert, you cannot compute inverse. So it will be a problem. Okay, and it especially happens when features are linearly dependent. Okay, in a matrix, okay, if there are two features, two columns same, okay, features are correlated, then you'll have this, you cannot compute this inverse. Okay. That means matrix is underdetermined. Mm. So, and second issue is that extremely large features are there, then yeah, it will take a lot of time. Okay, simple as that. And storing all data in memory is problematic. Okay, because when you compute this matrix X transpose X, then you have to store it, then invert it. Okay, and there is no online learning. You cannot learn in a sequential fashion. Okay, so this equation has lots of issues, and that's why we don't use it. And that's where we need iterative optimization algorithm called gradient descent. Okay, so that's what we are going to learn next. Okay, so idea is that first I will give the intuition and then I will go and touch upon a math a bit. Okay. All right. Okay. So far so good. I hope everyone understood that part, why solving gradient descent equation, cost function theta directly is not a good idea, especially for big data. Okay. Yes. Those who understood that part, please type as. Okay. Okay, great. Now we are moving to our iterative optimization algorithm called gradient descent. Okay, why we need it or what it is. Okay, now we have understood why we need iterative methods like gradient descent to solve for theta. Okay, so sadly, in my next slide, few slides, I have used W for the parameter, but don't worry, if you don't, if you're not happy with W, you can change this W with theta. So W is same as theta. So this is just a notation. Okay. So in practice, what is the essence of this optimization, or those who don't know what is an optimization? So goal is like this: given some function, okay, given some function, let's say this one, this is the graph of the function you plot, okay, and what you are looking for, a point W star at which the function achieves its minimum value. Okay, so in this case, if this is the domain of the function, and we are looking for a point in this domain of the function at which the function achieves its minimum. Okay, so that's called optimization. I mean, that's called minimization problem. Minimize the function f of or g of w, okay, with respect to w. Okay. So what gradient descent does, the way it works is like that at every point. So at every point you start, let's say at some point w0, okay, and you make a linear approximation, or to be more precise, you form a quadratic approximation in this at this point. Okay, you make a quadratic approximation, and then you actually optimize that function. Okay, so given this cost function or loss function j of w, we are looking for the point at which the function achieves its minimum. Okay, but we don't know at what is that point. Okay, so we use iterative algorithm that start with some initial point w0, and it moves towards, okay, after many iterations of this algorithm you will find this w star. Okay, so this is optimization is nothing but it's a search problem. Okay, we are looking for a point in the domain at which function achieves its minimum value. Okay, starting with some initial value w naught. Okay, and the way it works, it will form, let's say, okay, a straight line here, and see at what point this line hits the x-axis. Let's say this hits the x-axis w1, then it will compute another approximation at the next point here, and then it will go to w2, then next w3, and so on. Now you see that we are generating many points in the domain w1, w2, w3, and so on. Okay, so that's how this gradient descent actually works. Okay, we approximate the function in the neighborhood using quadratic approximation, and we optimize that quadratic function. Now, why we do quadratic approximation to a function? The reason is this cost function, this function, objective function, we call it objective function, is very complicated. In reality, this function could be horrible function. Okay, like e to power x into log x, theta, sine theta, whatever. Okay, very complicated functions. So we don't know how to compute the derivative of such a complicated function. Okay. So in this case, the optimization community says that instead of optimizing the given function, original function, directly you actually optimize the, you form a quadratic approximation to this function at a point and then optimize that function. Because I believe that all of you know how to minimize such a function. Let's say ax square plus bx plus c. All of you know this is quadratic equation. Yes. And how do you compute this minimum of this function with respect to x if you have to do it? Yes. People can type in the chat box. How do you compute the minimum? Yeah, you take the derivative with respect to x and solve it for 0. Okay. Yeah. All of you know how to take the derivative. How about this one? If I write tan h, sorry, tan, just a second. Let me write one function. I'm asking how to compute tan of cos inverse, then e raised to the power sine of log square x, something like that. Some horrible function if I give you and I ask you to take the derivative, can you do it? Okay. Yes. All of you realize that given any function which is very complicated, taking the derivative is not easy. Okay. Let's say even if you take the derivative, then solving that equation that you get is not easy. Yes. So that's the reason, given any cost function or objective function, what we do, we approximate. Okay, we approximate this function using some simple function whose derivative we know. Let's say we know already how to compute the derivative of this quadratic function. So we go ahead and approximate our objective function around that, around this function. Actually, I will show there is another slide that will give you more detail of this mathematics. Okay. So for the moment, you think of that we approximate any function with a given cost function with a quadratic function. We minimize that quadratic function. Okay. That gives us um, this just a second, actually that gives us actually this okay, when you optimize this function, eventually you get this update equation wt plus 1 equal to wt, sometimes written, I mean, remember w and theta is same in my notation, so don't worry, minus alpha times the derivative of the function with respect to w and the whatever function you are optimizing. Okay, so we get this gradient descent update equation. Okay, gradient descent update equation, like new value of w, updated value, you take the previous value, old value of the parameter and subtract, okay, alpha times the gradient or the derivative. Okay, you basically compute the derivative of partial derivative of your objective function, multiply that with alpha and subtract that value from the old value of the parameter. That is your gradient descent update equation. Okay, so I will show you where this equation comes from. Okay, so many people don't tell this. Okay, where this equation of gradient descent comes. Okay, I'll show you after we have done this slide. Okay, for the moment, think of that this is the update equation. Okay, in the next, remember this is an iterative algorithm. That means in every iteration or every run within the for loop, how to update or generate a new value of the parameter theta w. Okay, that's the idea. Fine. Is that clear what I'm talking about? I'll give you more intuition what alpha is and all in a moment. Okay. So let us take a concrete example, as I said, linear regression and run the gradient descent algorithm. Okay. So our hypothesis for linear regression is this. Okay. All of you must be knowing this one. Yes. Theta 0 plus theta 1 x. Okay. Given this hypothesis function, a prediction rule for linear regression, our mean squared loss function, cost function is this one. Okay. Fine. Now we are going to compute the, remember, in order to run gradient descent algorithm, what you have to do, you have to calculate the partial derivative of this loss function with respect to parameters. Okay, so you have to compute dl by del theta 0 and del L by del theta 1. Okay, so if you compute these two partial derivatives, set it to 0, then we'll get our gradient descent update equation. Okay, so let's see. I don't know whether you have seen this one. Okay, so this is the gradient descent update rule. Okay, this is the updated value. When you take the previous value minus alpha times the derivative. So you do it for all the parameters. In our case, in this particular example, we have just two parameters. If there are m parameters, you will have theta 2 also. Theta 2 equal to theta 2 minus alpha del L by del theta g 2. Okay. So basically you repeat this equation as many times as there are unknown parameters. Okay. But there is a concrete way. I mean, you can actually write one vectorized update equation for all the parameter using a single equation. You don't need less m equations. If there are m parameter, all of this can be written in a compact form. Okay. Okay. That would be another exercise. Okay. So let us compute. Go ahead and compute the partial derivatives. Okay. So we are going to do this. Okay. So partial derivative of the linear regression cost function with respect to theta 0 is this one, and with respect to theta 1 is this one. Okay. You can verify. Yes. Agree? People type yes if you understood this part, like taking the derivative is easy. You can do it. It is just a piece of cake. Or those who are finding it difficult, those who don't know derivative at all. I'm just looking at your chat. Please go ahead and type something. Mhm. Okay. I don't see any response. Either you are following or not following. So which one is true? Mhm. All right. Okay, I'm by default. Yeah, so the idea is that what we did, we took the linear regression objective function, this one, and we took the derivative. Okay. So if it is not clear, let me write it for you. Okay. Okay, I'm saying our, just a second. We get our, we need to compute the derivative with respect to this loss function. So let us go ahead and do it. Okay. So del L by del theta. I think we don't have much time for it, right? So this would be an exercise. Okay, I can go ahead and compute it. So I'm giving it that it's nothing but it's the derivative of this function. Okay, that we had written. I equal to 1 to n. Yes, theta x is nothing but theta 0 plus theta 1 x I minus yi square. Okay. So you need to compute the derivative of this guy, right? So if you take the derivative, so eventually what you get is this. Okay. So remember, this theta partial derivative will go inside the summation, and this is a square function. So derivative of x square is 2x, right? Similarly, we take this square, bring it to here, and theta 0 plus theta 1 x, xi minus yi, then 2 minus 1, and then we go within this bracket. We go inside the parenthesis and take the derivative of this whole thing with respect to theta 0. That gives us just 1. Derivative of theta 0 with respect to theta 0 is 1. Rest of the term will be treated as constant, right? That's it. So we cancel out this guy and this guy. So we get 1 over n summation and this term. Okay. Remember, this is our model. This part is our model. Yes, theta x I. Okay. Okay, and this is same as what is written over here. Okay, you see, this is same as there. Yes. Now similarly, if you compute with respect to theta 1, okay, you take this guy, same thing, but theta 1, change theta 0 to theta 1. So everything remains the same. When you take the derivative with respect to this inner guy, this one, you will get So this will cancel out with respect to theta 1, and with respect to theta 1, what you will remain is xi. Okay, theta 1, the derivative of theta 1 xi with respect to theta 1 will give you just xi. Okay, so that is what you see over here, xi being multiplied. Okay, fine. Now you have to set these equations to 0 and solve it for theta. Okay, that's another exercise. So Dr. Suren, if you're there, please note it down that audience solve these equations. Okay, they set these equations to 0 and solve it for theta. Okay, in order to get okay, very interesting. Actually, we don't need to set it to 0. Sorry for that. If you set it to 0, you'll get those equations for the update of theta 0, theta 1. But for gradient descent, you need partial derivative, these equation itself. Okay. If you set it to 0, you will solve for theta. That is your original equation. Covariance divided by variance thing I had written. Huh? So you'll get that equation. Okay. So you can also do set it to 0, solve for that, but we don't need for the gradient descent. For gradient descent, we need partial derivative, which we just did. So we plug those equations here in our this gradient descent equations. Okay. Yes, makes sense. People can type in chat. Okay, so here is the, let me show you the algorithm, the way it works. Okay, gradient algorithm. It's not just that complicated. What you need is just a for loop. Okay, and before for loop, you initialize theta 0, theta 1. That's a starting point with some initial value. Let's say 1, 1, 0, 0, whatever you want to initialize. Okay, and we are given some initial learning rate alpha and how many iterations you want to go through the data, and these are the data. Okay, and our output of this algorithm would be the updated value of theta 0 and theta 1. Okay, so we compute the gradient. Okay, we compute the gradient like we just did. Okay, and we use this update equation to update the parameters. Okay, that's a standard in gradient descent. Old value, you take the old value of the parameter minus learning rate alpha. Alpha is called learning rate, that I will tell you in a moment, and times the gradient. Okay, that's the gradient descent update equation, and you then run this loop many times. Okay, yes, everyone sees this gradient descent algorithm. Okay, so this is written in particular to linear regression, but you can use any mathematical function that you can optimize using gradient descent, as long as you can compute the derivative, partial derivative like this, then yeah, problem solved. Okay, fine. So having seen this linear regression algorithm, sorry, gradient descent algorithm. Okay, now we are going to look at the importance of the value of alpha. Okay, importance of the value of alpha. What is this alpha doing? Okay, so alpha is like alpha is called step size. Okay, learning rate, it is also known as learning rate or step size. It controls the size of the steps taken towards the minimum. It's like, let's say you are standing on a hill. Okay, you are a person standing on a hill. Let's say this is hill. Okay, you are on a mountain and you want to reach to the bottom of the hill. Let's say here, this is the bottom of the hill. You want to come here. Okay, the idea is to come down the bottom of the hill in the fastest manner possible. Okay, the question is which. Okay, so let me ask this question. Okay, you are standing on a Mount Everest and you want to come to the bottom of the hill. How do you choose? Or yeah, so what will be the approach to go to the bottom of the hill or Mount Everest in a fastest manner possible? Okay, so can anyone tell me, like, how do you decide? to go to the bottom of the hill. Okay, so what you have to do is you have to choose two things. One, in which direction I should actually descend. Okay, Amkar, yeah, Amkar is saying I will take a rope. So here, in practice, I mean, you are not given any. I can also choose helicopter, right? Chopper, okay, or aeroplane. That's not the point. The point is that you don't have anything, chopper, rope, and all that. You have to go. You have to basically use your feet. Okay, so what you have is basically which direction should I pick? Because some direction can take you up the hill. Okay, let's say you are not on the Mount Everest, which is the tallest point, but you are somewhere. Okay, you are stuck somewhere, but you want to go to the bottom rather than up. Okay, so you have to choose a direction which takes you towards the minimum, the bottom, and how big the steps taken is. So these are the two factors that decides how fast you reach to the bottom. Yes, which direction and what step size. Let's say there is a baby with you, and you are also both of you want to take go to the bottom of the hill. So who will reach faster? Obviously, the person who takes a bigger step. Right? A baby takes a baby small baby step, very small step, right? So baby will take more time than you to reach to the bottom. Yes. So that's the role of alpha in our optimization algorithm. Okay, having very small value of alpha will take a lot of time to converge. To go to the bottom of the hill, it will take a lot many iterations. If you set alpha too small, like baby step. But if you take alpha a very large value, then it might overshoot the minimum, fail to converge. What does it mean? If you run very fast because of this momentum, okay, inertia, momentum and all, what will happen? You might miss the bottom and you might go to the another hill. Okay. Yes. So that's the thing with this alpha. Okay, this is the here. Let me show you the picture. So this is our objective function that we want to minimize, and minimum is here. Okay. And let's say you are starting from here. This is your W naught. Okay. If you set alpha very large, okay, really big, then W will go here. Okay. And you will miss the minimum. Okay. And then another step will be here. Okay. And you will basically fluctuate. Okay. You will fluctuate around the minimum rather than converging to the minimum. You will fluctuate. Okay. You will go up and here and here. Okay. And if you take alpha is really small, then you will descend very slowly, like this, towards the minimum. Our objective is to come here. Okay. So yes, moving towards the minimum, but very slow. So it will take a lot more iteration than required. So the idea is to pick the alpha learning rate such that you go to the minimum, but you do not overshoot it. You do not miss it. That's the goal. Okay. So that's the role of alpha, what it is doing there in this gradient descent. Okay. All right. Now you might ask, when should I stop the algorithm? Okay, my algorithm is running fine. How should I decide when should I stop my algorithm? Okay. So there are many actually stopping criteria for the algorithm. So one way to decide when to stop is like this. You compute the loss in the previous step and the current step and take the difference, the loss value or objective function value. If the absolute difference is less than a predefined threshold epsilon, then you stop. Okay, that means my loss is not changing too much. That means when you have reached to the minimum, then loss will not change much. Okay, then you stop. Alternatively, you can also stop after the fixed number of iterations. Let's say you cannot afford more than 10,000 iterations, so you'll stop after that. Okay, so that's the idea. Fine. So yeah, I think this visualization I have already Here is the visualization of gradient descent. Okay. So on your screen is what is shown is these are the contours. Okay. Contour plot, what we call them. And yeah, and the gradient descent is starting over here and it goes towards the minimum in, let's say, few steps. Okay. That's how gradient descent moves. Okay. Actually, I have one more picture, one more slide to tell you this thing. So final remark for a gradient descent is like this. Gradient descent is a powerful optimization technique for solving linear regression or any other. In general, it is can be used to optimize any loss function. Okay, especially for large data. For small data, you use that normal equation: x transpose x inverse x transpose y. Okay. Choice of learning rate number of iteration is also very important. Okay. And it can be extended to more complex models used in machine learning, such as logistic regression and neural network. Any of the model you can optimize using gradient descent. Okay, so that's the power of gradient descent. So, so Dr. Surendra, if I have time, then I can show another slide for 10 minutes to give more intuition.
Yes, sir.
Okay.
No issue, sir.
Okay,
Yes, sir.
fine. So let me go to my drive. Okay, sure. Yeah, this one. So this slide will have give you more mathematical intuition and pictorial intuition also. Okay, so this is part of my optimization course. So I thought to include it here as well. Okay. Um, and I think in my talk there was mentioned that variants of gradient descent. Okay. So many of the so gradient descent is one optimization algorithm. So there are many other variants of it which use gradients to optimize functions. So there are called first order method and second order method. So gradient descent is one, and then we also have second order methods which use, what is second order means? They use second derivatives like Hessian, such as Newton's method and quasi-Newton method. So they are also a gradient based method. Okay, first order and second order. So people can also use Newton's method. Okay, so gradient descent. Okay, so you might ask why we choose, anyone can here tell me why we use gradient to gradient direction. Why it not takes us to the, let's say, top of the mountain. Okay, rather than why it brings us to the bottom of the hill, not upward the hill. I mean, choosing the gradient direction. Okay, so those who think they know something, so you can tell me why we choose gradient direction to go to the bottom of the hill. Any ideas? And now you see this equation. Right? So in our equation, Wt plus 1 or theta, whatever you want to call it, Wt minus alpha, and then we have this gradient of the function with respect to W, right? So why we choose this gradient direction? When you are on the top of the hill, you are choosing the gradient direction to go to the bottom. So why we do that? Not any other direction. Yes, there's many other direction, right? Yeah, so all of you are saying gradient gives direction of maximum change. Very good. Yeah, so remember that gradient at a point, okay, gives you the direction of the fastest or maximum increase in the function value. Okay, gradient gives you the direction of maximum increase of the function value. And why it is so? Here is why. Look at this function that we want to minimize. F of x is any function. Okay, so change in this function f can be written using Taylor series approximation. I hope people know what is a Taylor series. Those from engineering background, they might be knowing Taylor series. So this is nothing but Taylor series approximation up to the second term. Okay. And in this, G is the gradient and H is the Hessian. Okay. H is the Hessian. Hessian contains second derivatives. Gradient contains first order derivatives. So this is the Taylor series expression for the function, and in this, if delta, which is a vector, is very small, then change in this function f denoted by delta f would be approximately equal to G transpose delta. Okay, change in this function. So what will happen when delta norm of the delta is 0? So this term actually vanishes. Okay. This term is bounded by, this term is actually less than or equal to delta square. Okay. This term is actually less than or equal to delta square if I set Hessian to be identity matrix. If the H is set to identity matrix, then this term would be like this. Okay. And their norm is going towards 0. Norm of this vector is 0. So this term will become 0. And since we are measuring the change delta f, so this delta f would be say equal to this term only. Okay. Yes, everybody agrees with me that delta f is almost G transpose delta. This delta, small delta. Anyone here who is following up to this point? This is very crucial to get the gradient descent. Okay. The second term finishes and we are measuring the change. So change is nothing but f x plus delta minus f of x. This is the change between the current function value and updated function value. Okay. This change is nothing but delta f. Delta f, and that's how you get this term G transpose delta. And here is the picture. Let me show you. Look at what is going on. So this is the contour plot. Contour plot is nothing but basically we take slices. Let's say I have taken a bowl, okay, or a ball. If I take slices, if I slice at this level and this level, okay, what you will get? If you slice a bowl, what you will get? You will get circles. Yes. If you slice a bowl at many points, you will get circles. Yes. And these are the circles plotted on your screen. And on a circle, at everywhere, value of the function will be the same. That's the definition of contour plot. Okay. On a circle or levels, we also call it contour or level set. So on a level set, function value is the same. Okay. Now look at this point x. Okay, and we make a small movement in the direction of delta. Okay. Let me zoom it for you. Look at this picture and what we are doing. We are at a point x. Okay. We are at a point x and we are moving a small amount delta. Basically, we are using the definition of derivative. Okay. In the derivative, we change the function value by a small amount delta. Okay. So new delta, this would be your x plus delta point, right? But when you move by delta and delta is really small, what is happening is change in the function value should be negligible because on the levels on this contour plot, function value will be the same. So even if you make delta, which is very small, change in the function value is 0. Yes. Everybody with me? Change in the function value. If I move by a small amount delta on a same contour line, it will be the same. Yes. People type yes if you are following this point. If I move a small amount of delta, my function will not change. Yes. It is because function value is same. Now this delta is 0 and we use the definition of dot product of two vector. Dot product of two vector is given by x transpose y is norm of x, norm of y cos theta. This must be familiar to you as well. Yes. And this term is 0. This term is 0. Okay. This term is 0. Then what does it mean? What does it mean? Dot product of two vectors is 0, right? That means two vectors are perpendicular. Yes. That means in our case, these two vectors, g vector and delta vector, are perpendicular. And if you see, this delta vector is here. So g will be either in this direction or this direction. Yes. Orthogonal or perpendicular. Now you see this gradient. So this g is our gradient and g is perpendicular to the contour line. Yes. That's the definition. Now in this contour line, if you see gradient direction, okay, positive direction, okay. If I move in this direction, function value is increasing 40 to 50, right? If I go opposite direction, function value is increasing. Everyone see that? This is the very important slide. Why gradient is always perpendicular to the contour line and why we move in the negative side of the gradient. You see, if I move away from the, up, okay, from 40 to 50, function value is increasing in the positive gradient direction. In the negative gradient direction, we are function value is increasing. And since we are dealing with minimization problem, we want to go into the negative direction of the gradient. Okay, so that's why in our equation, you see, we have this Wt plus 1 equal to Wt minus, rather than plus, minus alpha times the gradient. Okay, that is the reason we use or move in the direction of negative gradient. Okay, everyone see this picture? You can tell me now why we go. Remember, this is the function value at which the function value is the 0. So this is the minimum point, or in this case, a bowl function, this is the minimum point. That's where we want to reach. Okay, and we follow the negative of the gradient direction. That is the reason. Okay, so yeah, so with that I will stop. I had one more slide. This what I actually was okay. Yeah, so this is the picture of the bowl. Okay, and we go in the negative side of the gradient. You see, this is intuition in 3 dimensions. Okay, and yeah, so that is our x star minimum point, and we go in the. So this actually this slide has a different notation, but I will stop here there only. Like now you know the equation of the gradient descent, update equation, and why we go or choose the negative side of the gradient descent, gradient direction. Okay, so I will stop here. I think otherwise we'll delay our second, or maybe I think we can take a break and then we'll continue discussion on this gradient descent. Yes, in the demo part, and then I'll show you some code also. Okay, so that you will after that lecture, I think you will know everything about gradient descent that you need to know. Yeah, I think it's time for break.
Yes, sir. So
Okay.
we can take a 5-minute break, sir. Then
Mhm.
next you start your next session as per
Yeah.
your convenience. Yes, sir.
Okay. Hello.
Hello. Yes, sir.
Yeah. Okay, now I have see that there are a few questions. First question is why we need to go to the center. Okay, very good. Let me share my screen again and then I'll explain all of it. Okay. Okay. Let me explain all of it. Okay. So we were on this slide, right? And yeah. So I think that part is clear, right? Why we are going in the negative direction and why we are going to the center. Why we are going to the center in a moment, I'll talk about that. Okay. So, okay. So I think Gitanjali has already answered. We want to go to the minimum. Yes. We are going to the center because see, in this blue bowl, right? So we are taking this, we are cutting this bowl, right? So these are the, if I cut a bowl, I will get circles. Circle or ellipses, what you want to call it, right? Yes. So these circles are plotted on this, in this figure, okay? And in this circle, the smallest circle will contain our minimum point, yes or no? So this will, so if I cut here, so I will get the smallest circle, yes? So this circle has the minimum point, not? This has the minimum point in this function, yes? And this plot, this circle is actually here. So this circle contains the minimum point. So that's why we are going toward the center. Okay. Yeah. Okay. And okay. Now it is clear that we are why we are going in the negative direction of the gradient because it takes us towards the minimum. And if we wants to go to the maximum, let's say sometimes we have maximization problem, right? In that case, you have to choose this direction. Okay, this other direction. So you have to do plus rather than minus. Okay, so be careful. If your problem is maximization problem, then you have to do plus rather than minus. Yes. Okay, so be careful. And this also shows why gradient is always perpendicular to the level curve or contour line. Okay. So if from today somebody asks you why gradient is always perpendicular to the contour line, show them this picture and this equation. All right. So yeah, so this slide also has the gradient descent algorithm, but it is general. Earlier algorithm was specific to linear regression. Okay, because we are optimizing the linear regression cost function. Okay, but gradient descent is a general algorithm and using which you can optimize any objective function, any loss function. Okay, so let's say we have this problem: minimize function f of x. Okay, so this is saying that give me the minimum point x at which this function achieves its minimum. Okay, so how do we do that? General algorithm looks like this. You choose a starting point x naught. Let's say this is my function, general function. You start at initial point x naught. Okay, then epsilon is your threshold to check something. I'll tell you in a moment why what we are doing. And k is our iteration number. Okay, first iteration, second iteration, and so on. Okay, after the algorithm terminates, it will give this x star. Okay, our goal is to reach x star. Okay, so what we are doing, we are running the while loop or for loop, whatever you want to call it, while alpha x, alpha k dk norm of that term is less than epsilon. You choose the negative of the gradient. Dk is nothing but what is it is saying choose the direction dk which is negative of the gradient of the function. Okay, and I have already told you why we are choosing this direction. Yes, and we perform the line search. This is something that was not there earlier in gradient descent. So this actually line search is done in order to find the optimal value of alpha. Okay, so earlier when we are discussing, then there was this slide now, like how, like too big value or too small value of alpha. Okay, too big value is problematic, too small value is problematic. Then how to find the right value of alpha? Okay, if somebody asks you, then you can do, I will do line search. Okay, so there's actually another algorithm within this one that gives you the optimal value of alpha. But in practice, like scikit library and all, they rarely perform line search. So usually people do grid search and choose the value of alpha k in some range. Let's say 10 to the power minus 6, 10 to minus. They will run the algorithm for various values of alpha. Okay, in this range, and choose the value of alpha that minimizes the function in, let's say, smallest number of iteration. Okay, or if you want more sophisticated algorithm for choosing the alpha, you can do line search. Okay, but I will not go into that detail. Okay, and then finally line number 4, you see what we are doing. We are using our gradient descent update rule. Okay, we are using our gradient descent update rule. Previous new value is old value plus minus alpha k dk. Dk is already negative, so it will be xk minus alpha k gradient, which is again same. Yes, everybody see that what we are doing? Any doubt? I'm looking at the chat. Yeah. Any question? Okay. So you can ask, what is this doing, right? This term. So this is actually stopping criteria. So in optimization, iterative algorithms, there are many optimization criteria or stopping criteria, and this is one of them. Okay. This is nothing but it is checking the norm on the gradient. Okay. If the gradient norm is less than gradient is very small, basically what you are doing, you see, you take you in this initial value x, you are adding some term. That term is alpha k dk. In the old value, you are adding some term, and this addition of the term is the norm of this value. Absolute value of this term is very small, then you have stop this algorithm. That's what it is saying. If the term I'm adding to the old value is really small, then stop the algorithm, because it is not going to change much. Okay, you will not get very different value of x. Okay. All right. So pictorially is like this. Say you start your algorithm here, x0. Okay. Do not get confused with sometimes I'm using x, w, theta. So this is my optimization variable that I care about. Okay. So this algorithm, okay, let me give you something. Okay. So look at this picture bowl example that I was talking about, right? So this is this bowl, 3-dimensional. So if I take the slices, I will get these concentric circles. Okay. And in this circle, you see, if I move in this bowl surface somewhere, okay, my function value will change if I go up or down, but if I remain in the same level, my function value will not change. Now you see these pictures, two bowl, this picture and this figure, and see why gradient is perpendicular. Okay. That was like mathematical proof, and this is geometrical proof. Okay. And why we are moving in the negative direction of the gradient. Okay. Okay. So here is another stuff that we want to highlight. So let's say how this algorithm actually works in practice. So we are in the beginning at this point. Let's say this is our x naught. And remember, in the previous old value x, we add term alpha d. D is our direction, with this nothing but gradient direction. In this old value, we add alpha d. Remember, when we add, remember d is our vector, alpha is a scalar. Okay. So if you really add a big value, alpha plus d in this old value, this might go here. Okay. Away, very away from the minimum. But if you choose this value, alpha, now you see, d is kind of vector, gives you the direction. Alpha decides how big my step size would be. Okay, so in this, if I choose really big alpha, it will go here, very far away. Okay, because this is the magnitude. Alpha you can think of as a magnitude of this vector. Okay, so if I choose proper magnitude, then I will stop here only. Yes, I will stop here only because my vector length would be small. My state size is small, so I will stop here only. So my new value, updated value of x will be this one, which is close to minimum. Yes, everybody see that? I will be very close to the minimum. If I choose alpha is small enough, not really small, but good small. Yes, people type yes that you followed this at this point. Okay. Now you see everything making sense. Now why we are choosing negative direction of the gradient and what is the role of alpha? Yes. If you choose really a big alpha, so this line that you are adding to the old value of x, it will really be away from the minimum. Okay. So that's what is going on in gradient descent. Okay. Now here are the variants of gradient methods. Okay. So in optimization, there are many gradient based methods. Okay. Gradient descent is one of them. Okay. So let me tell you. I mean, after this lecture, you will note at least 6 gradient based methods. Okay. In the same update equation, right? W or X E plus 1, xt plus alpha k dk. If you choose the direction dk, okay, differently, then your algorithm will change. Okay. So what people have done, innovations, somebody said, okay, if, let us set dk like this, where dk is nothing but a Hessian matrix. Okay, Hessian times the gradient. Okay, then this is called scaled gradient descent method. Okay, but if you choose in the Newton's method, we set this direction dk as the inverse of the Hessian. Okay, in Newton's method, if you see this direction dk is set as the inverse of the Hessian. Okay, so those who are familiar, I think in BTech first year we study this. Okay, alpha times the gradient times the second derivative, that is your Newton's method. Okay. Here I have put Hessian. If you set in this equation dk as the inverse of Hessian, then it is Newton's method. In quasi-Newton method, we approximate this Hessian matrix. There you see this is dk is approximate value of the Hessian inverse. Okay. In steepest descent or gradient descent, we set dk equal to Hessian is identity, because in gradient descent you don't use Hessian, we use only gradient. Yes. Okay, then there is diagonally scaled, discretized Newtons. So depending on how your decay is, okay, you get many algorithms. Yes, all of you see this? Like various forms of algorithms are formed based on this Hessian. Okay, approximate Hessian, inverse Hessian, this, that. So all of them are coming. All right. Okay. Anyone here who doesn't know what is a Hessian? Let me see. Anyone here who doesn't know Hessian? Hessian is a matrix. It's a positive, definite, semi-definite matrix that contains partial derivative of second degree. Okay. Gradient contains partial derivative of first degree. Hessian contains partial derivative of second degree. All right. Now, the crux of the gradient descent. The equation that I have shown you earlier, this equation, you might ask, where does it come from mathematically? Can you show mathematically who derived this equation? Where does it come from? Okay. All right. So this equation, yeah, so those who don't know Hessian, forget about it. We don't need Hessian. Okay, but gradient or derivative, partial derivative is same. Okay. So anyone here who doesn't know gradient at all? Because otherwise this lecture will not make sense if you don't know what is a gradient. Anyone here who doesn't know gradient? Please type something. Okay. Type S if you know gradient. Okay, Gitanjali knows. Anyone else? Amkar, Brahma. Okay, very good. How about other people? We have around 25 to 30 people. Okay. Okay, fine. So, okay, now let us derive this gradient descent update equation. Okay. Would you be interested in knowing where does this equation come from? Many places you see this equation. Yes. Okay. So that equation comes from here. So at any point X, okay, let's say this is your curve, complicated function we don't know that we want to minimize. Okay. And so the gradient descent does at any point, what it does is at a point X naught, it will form a quadratic expression, quadratic approximation to this function like this. Let's say quadratic approximation of this function at this point is like this. What is a linear approximation means? You will use a line to approximate this function like this. Quadratic approximation will approximate this complicated horrible function using second degree polynomial, which is like this. If I if I plot ax square plus bx plus c, it is nothing but equation of a parabola. Yes, it will look like a parabola, something like that. Okay, so quadratic approximation is like this. So intuitively, if when you want to optimize this function, you're looking for the minimum. In reality, we are looking for the minimum of this rate function, okay, which could be anywhere, we don't know. What we do in practice, we take the approximation, this second degree approximation using Taylor series, and we minimize that function. That gives us the this gradient descent update equation. That's where this equation that you see, that's where this comes from. Okay, I'll show you in a moment. So let's say this is my second degree approximation, Taylor series. Those who know Taylor series, they can easily guess. F of y equal to f of x plus first degree, sorry, first derivative 1 y minus x plus 1 over 2 alpha y minus x. So in a quadratic or second degree Taylor series approximation, what we have done, we actually second term is nothing, it contains the Hessian. Okay, let me show you in my browser. Okay, let us see in Taylor series approximation. Okay. Just go to the Wikipedia and just recall your memory so that uh, yeah, so we are talking about this Taylor series, and okay, so there are various forms of Taylor series. Okay, so we are looking for, so this is Taylor series in a scalar variable. We are looking for Taylor series in a vector. Okay, Taylor series in a several variables. We are looking for this one. Okay, so yeah, so this is the equation we are looking for. See, Taylor series around a point A, f of a x minus a, transpose first derivative, then plus 1 by 2 factorial x minus a transpose, second derivative x minus a, and so on. Okay, so we are using this equation. Okay, just to correlate it with everything, we are using this equation. There we are using y and x. Here it is, they have used x and a, so don't worry about that. Okay, fine. Okay, where is it? Just a second. Yeah. So we took the second degree Taylor series approximation, and we are going to minimize this quadratic function. Okay, we are going to minimize this function. Okay, so and see the way minimization is done is very intelligent. So as an exercise for you would be you go ahead and minimize the way you want. Okay, in fact, I will show you a very different approach. Okay, so this is what we are going to do. We are going to minimize this function with respect to y, because y is our updated value, new value. We are looking for new value from the old value. X is my old value, and how should I? What should be our updated value y? So we are going to minimize this second degree polynomial quadratic approximation. Okay. So this is fine. So far, so good. This is nothing but gradient times y minus x plus 1 over alpha. Here we have replaced the Hessian with 1 over identity matrix and 1 over alpha. Okay, that's how we get this term. Okay, now in this function, you see, in this function, we are going to minimize with respect to y. So this term can we get written off, because this function does not depend on x. Because we are minimizing with respect to y, so all the terms containing only the x can be get written off. So this term can be get written off. Yes, all of you look at this very carefully, how the gradient descent update equation comes. So this term is gone because it does not contain y. This term is also gone. Okay. Now we can write this term like this and this term as it is. So far so good. No issue. Okay. So this angle bracket, remember this angle bracket is shorthand for this thing, gradient transpose y minus x. Okay. And this can be written as gradient of x into y minus gradient of f into x. Okay, and this term does not contain y, so we have cancelled this. So that's why you see only y term, no x. Okay. Now we multiply this whole thing with 2 alpha. Okay, so you have this 2 alpha coming here, and now 2 alpha is gone from here. Okay. Now we are going to open this norm equation. This is nothing but it's like what is the a minus b square. So you write a square plus b square minus 2ab. So that's why we are doing. A square b square minus 2ab. Okay. We open that square term. Now this whole thing can be written like this. Okay. This whole thing can be written like this. This is an exercise. Dr. Surendi, if you are here, then you please ask the audience to compare these two equations, equation number 1 and 2, so that they can see how we get equation 2 from 1. Okay.
Okay.
Yeah. So it is nothing but is completing the square. Okay. So we ignore some irrelevant term also. Okay. For example, if you open this, you will get norm of y square. Okay, this term you will get. Then if you open this whole square, you will get norm x square plus additional term you will get is alpha square and norm x square. That can be ignored because that contains x, so it has no contribution, right? So you can add additional term, like we can remove constant term. So similarly, we can add constant term, right? In the optimization problem, not an issue. Then it will give us 2 times x minus, sorry, 2 times y into x minus this whole thing. Okay, so if you open this, you will get basically this equation number 1. Okay, now if I ask you what is the minimum of this function, okay, all of you look at equation number 2 and tell me what is the minimum of this equation. Okay, it's like, okay, so give me the value of y that minimizes this function. So obviously norm is always positive, right? Norm or absolute value is always positive. So this function will achieve its minimum when y is same as this thing. If I set y as equal to x minus alpha times delta y gradient x times alpha times gradient. If I set this y as same as this term, then this will vanish. This whole thing will become 0. So this function is positive, so it will minimum will be 0. Now you see this equation, and this is nothing but that is your gradient update equation. X plus is nothing but updated value of y is x plus. Okay, updated value of the parameter is nothing but old value minus alpha times the gradient. Now you see that's where this gradient descent update equation comes. Okay. It's not like some magic thing happened. Somebody wrote this thing, but everything in math has logic. Okay. Yes, people can write S or yeah, if you have followed at least this point. Okay. Let me know. Okay. Great. Amkar Brahma. How about others? Those who have understood this part, minimizing a quadratic function. Fine. Here is a picture. Those who are not following, here is a picture. So in this picture, this is the function plot we want to minimize. This is like this red function I had written, and this is complicated function. And this function is being approximated using a quadratic function at this blue point. At this point, we are approximating using a quadratic function. So it looks like this. And we are minimizing this quadratic function, and minimum is at this red point. Okay, we approximate the function at this blue point, and minimum on this quadratic function is this red point. So from the blue point, we want to go to the red point. So how to do that? You do this. You minimize this quadratic function. That gives you the gradient descent update equation. Okay. That gives you the gradient descent update equation. So here is the approximation. Intuitively, let's say our function is the blue function. Okay, and look at the role of eta. Okay, what eta is doing. Okay, if you use eta 0.2, you get this green curve, green approximation curve. If you set eta, sorry, now my bad. This eta is nothing but alpha. Okay, this alpha step size. Okay, if you use a small step size, your quadratic approximation would be this green curve. If you use large value of alpha, your quadratic approximation will be this red curve, this one. Okay. Now you see what is the role of alpha playing here in terms of approximation. Yes, everybody sees that. Now if you change the alpha, the function you are minimizing or optimizing will be different. Yes. Everybody see that? We are optimizing this quadratic function, and the role of alpha plays a significant role. Okay, because the minimum of green function and red functions are different. Okay, so that's what will happen if you change the alpha differently. Okay, so this slide will tell you everything about this step size. Okay, my bad, I am using this tk as a step size. Okay, but tk is same as alpha, so don't worry. So if you set alpha really large, so you will bounce back. You will bounce back, move around the minimum, and it takes many steps to converge. Okay. If you set alpha really large, okay, and if you set alpha really small, baby step, so many small steps will be taken to reach to the minimum. Okay, see, this is what happens. Okay. And if you set step size alpha just right, in few iteration algorithm will converge. Okay, algorithm will converge very nicely. Okay, so that gives all about the details of gradient descent. Okay, now okay, so as an exercise, I hope all of you have some papers. All of you can take out some papers and do this exercise. So I'm going to write a function f theta. let's say that my function is theta minus 2 square. Okay. So you optimize this function with respect to theta and give me the gradient descent update rule. Okay. All of you, as an exercise, you do this. Given this function, optimize this function with respect to the gradient descent and compare your value using the direct optimization, because this is quadratic function. You can optimize this directly using calculus, right? But what you do, optimize using gradient descent, taking the initial value of theta as, let's say, 1, and number of iteration you run this gradient descent, let's say 5. Okay. And you also verify the minimum value using direct calculus. Okay. All of you run gradient descent for 5 iterations starting with theta 0 equal to 1. Okay. Yeah. So I'm waiting for your answers.
Sir, learning rate, is there any value of?
Yeah. So learning rate, I forgot to give the learning rate. You can choose alpha as, let's say, 10 ki power minus 1, 0.1.
0.1. Okay, fine.
So basically what you have to give me, you give me theta 4 here. Okay. So you'll get theta 0, theta 1, theta 2 as well. Yes, participants can type their values of theta 0, theta 1. Theta 0 is already given, theta 1, theta 2, theta 3. Okay, so that would be fine. Mhm. Okay, so anyone can tell me the gradient in the first iteration? What is the gradient value at theta 0? Or theta 1 is 1, so basically your gradient will be minus 2. Okay. So gradient in the first step should be minus 2. That is evaluated at theta 0. Okay, and that value we plug. Okay, so you see 1 minus 0.1 times minus 2. So you should see the equation like this. Okay, that is equal to 1 plus 0.2, that gives 1.2. Okay, so your theta first value should be 1.2. Those who have got 1.2 is the correct. Okay, so in this equation which I typed, right, so I'm using the, okay, so here is what is going on. uh, See, okay, so basically we have to plug the value theta 0 minus alpha times the derivative gradient of the function. Okay, so theta 0 is initially 1, alpha is 0.1, and gradient, if you see, gradient is nothing but 2 times theta minus 2. So in this we have to plug the value of theta, which is in this case 1. Okay, so in this equation, gradient equation, if you plug, you will get minus 2. Okay, that's how you get 1.2. Now you use this updated value 1.2 in the second iteration. So this is my iteration number 1, 2, 3. Now 0.1. Now you have to evaluate your gradient at this point. This is my new value, right? So this value you plug here. Okay, so you'll get 2 times 1.2 minus 2. That is nothing but 0.8 minus 0.8. Okay, minus 0.8, which is nothing but you get 0.16. Okay, that gives you how much? You add 1.2 plus 1.6. This is 1.2. Sorry. Okay. So those who have got this value, then something like this. Okay, then in the next step, this new value will come here, minus 0.1 into, then evaluate your gradient at this point. Okay, so now this value will be used to plug here. Okay, yeah, and you will get the value as yes, here you will get 1.28 if you use the gradient, and finally it should be 1.488. Okay, then in the next iteration, 4 and then 5. Okay, in fourth iteration, 1.488 minus 0.1 into, here you should use 1.024, something like that. I don't know. I mean, I'm just maybe. Okay, so you verify 1559, then 1.59 minus 0.1 into minus 0.819. Then finally you get 1.67, something like that. Okay. So those who have got something like this, you're correct. Okay. So now see what is going on. You look at the calculus method. Let us use calculus. Okay. So here gradient descent after 5 steps is giving us the value of 1.67. Now let us use calculus to optimize. According to you, can anyone tell me, if I optimize that function with respect to theta using calculus, what is the optimal value? Optimal value for this function if I optimize using gradient descent. Sorry, calculus. Anyone? Theta minus 2 squared. What is the minimal value? At what point this function achieves minimum? My God, Gitanjali, you're saying 0? It is a square, right? It's a square function. So a square function, yeah, minimum value is 0. And what is the point? At what point this function gets minimum value? 2. Very good. Gitanjali is brilliant. Okay, so now this C, after if you run more iteration, you will see this value going towards 2. Optimal value is 2. So gradient descent will slowly go to optimal value, theta star, remember? W star. So 1.6, every step it is getting better, right? This is close to 2. In the next iteration is get better and better. So more iteration you run, the gradient descent will give you a value which is close to 2, which is optimal value. Okay. So that's how gradient descent works. Any questions? I hope they should be fine. I mean, running gradient descent is like very simple. Okay. And now same thing you can code in Python. Okay, so I'll share at the end of the whole session, I'll share some PDF and Jupyter notebook which contains the code, which you can code and plot and see how the things are working. Okay, fine. Okay, so that's it. I'll take a break here for this session and conclude my lecture on gradient descent. We should initial theta values. Yeah, I mean, you could choose any initial value. It's up to you. You can change now. You can change the value of alpha and do this calculation and see. Okay, and you can also choose theta 0 equal to 100 also. It's up to you. Farther away you take this value in the initial value, the more steps it will take. If you see set this theta 0 to 100, see how many iteration it takes to go to the optimal value of 2. It will take more large number of steps. So that's why initial starting valuations and alpha is very important. Okay, what value you are taking. Yeah. For fundamental and applications, you can refer any optimization book. So George, like for fundamental, there is an introduction to optimization in one variable that I find really awesome book. After a lot of search, okay, so this gives you very good flavor of optimization just using scalar variable. It does not deal with high dimension like in 2D, 3D, but it deals with 1D, like scalar variables. Okay, so you can refer that book. Optimization using introduction or optimization using one variable, something like that. Okay, I'll share that name later. Actually, I don't remember that exactly, but there are other books I remember for optimization. Book. So people use this by George Nociden. Okay, and see if you just type in Google, you'll get this book. Nociden book, George Nociden book. Book name is I think Introduction to Optimization or something like that. Okay, for convex optimization, author from Stanford. Book name is Convex Optimization. This is very advanced book. Okay, so you can also refer this book, Convex Optimization, by Stephen Bayard. Right? Okay, that's it. So thank you, Dr. Surendra. I think there is no more questions. So I'll stop.
Yes, sir. Thank you. Thank you for such a wonderful session, sir. Just you just gave some little questions for practice also, this gradient descent and this intuition behind this gradient descent, mathematical expressions, everything that you gave. Thank you very much, sir. So in the next session that we will see some kind of hands-on.
Yeah, we'll come.
Okay. So sir, next session that we will start at 2 o'clock,
Mhm.
2 to 3, and maybe 5 to 10 minute break if you want. Then the second means hour, 3:15 to 4:15, or it's up to you.